I am so glad you're here because today we're going to be learning all about matrices and character tables when we talk about group theory and inorganic chemistry. In a previous video, which you can view here, we talked about all of the different symmetry elements and symmetry operations when we're thinking about group theory and symmetry in molecules. Recall that one of those symmetry operations was a C3 rotation where you rotate 360 degrees divided by 3, which is 120 degrees, around an axis. In this case, the axis would be going through the nitrogen atom, and you do a 120-degree rotation, which moves the positions of these hydrogens. So I've placed 1, 2, and 3 at their original positions, and now they become 1, 2, and 3 following that 120-degree rotation. Now, importantly, that transformation or that symmetry operation actually corresponds to some sort of mathematical operation. In fact, we can use linear algebra or matrix algebra to define what sort of operation is occurring. And then once we've identified the mathematical operations that are occurring during symmetry operations, we can assign the different groups of symmetry for different molecules and identify what are called character tables, which help us easily identify what sort of mathematical operations are possible for different objects, or in the case of chemistry, molecules. And make sure to stick around to the end because I have some practice problems that should help for your next exam. A matrix is an order array of numbers like both of these examples. In the first example, we have what is called a 2 by 2 matrix because it has 2 rows and also 2 columns. Importantly, matrices can be constructed of any number of rows and columns. For example, this is also an example of a matrix, except this one is 1 by 1, 2, 3, 4, 5. So we would call this a 1 by 5 matrix. In fact, we can even have matrices that are just a single row and a single column, and we would call that a 1 by 1 matrix. In a linear algebra course, you would have learned that you can actually do things like multiply two different matrices together. And when you do that, you're using the rows and the columns of a matrix in order to determine what that new matrix after you multiply them together would be, or the product of that multiplication. And we do this by considering both matrices, the rows and the columns, following a relatively straightforward order of operations. Let's consider a relatively straightforward example where we take two 2 by 2 matrices and we multiply them together. I've tried to color coordinate them so that you can follow along more easily. We're actually going to add, term by term, the product of the rows of the first matrix by the columns of the second matrix. Remember, we're multiplying the rows by the columns. So we're going to start with the first 1 right here, and it's going to be that 1 times the number 7 of our second matrix. So 1 times 7 goes first. And since now we're moving to the second column of this number 5, we're going to have a 5 times the 4, which comes from the second row of the second matrix. So then we would take the sum of those values, and that would be our new first digit that would go in this matrix. For the new number that's going to go at the bottom left-hand side of this matrix, we need to take this 2, which is the first number in this row, again times that same number 7. So then we're going to add it to the 6 times the number 4, which is on the second row, but on the first column of the second matrix. And that number is going to be 6 times 4. And that gives us, after we take the sum, what that value is going to be in this bottom left-hand corner. So now moving on to the top right-hand corner, we're still going to start with this first row because remember, it's the rows times the columns. So in this example, we're going to have a 1, and that is going to be multiplied by the 3 from the second column of the second matrix. So 1 times 3. And then remember, we're taking the sum. So now we'll move on to the 5. So we're going to have our 5 value, and that is going to be multiplied by the 8 value, which came from the same column. So 5 times 8. And now we just have one more position to satisfy, and for that we're going to start on the second row because we're filling in the second row, second column. Therefore, we're going to be using the second row and the second column. So then here we're going to take 2 and multiply that by the 3, which came from the second column of the second matrix, and that is going to be added to 6 times 8. So that's going to be 6 times 8. And that is going to give us all of our values, and now all we need to do is add these values together to get our new matrix. Now, importantly, anytime you multiply two matrices of the same ilk or the same kind, in other words, a 2 by 2 times a 2 by 2, your final matrix should also be a 2 by 2 matrix. So 1 times 7 plus 5 times 4 gives us 27 because we have 7 times 20. So this value is going to become 27. 1 times 3 plus 5 times 8 is going to give us 43. So that number is going to be 43 there. 2 times 7 is 14. 6 times 4 is 24. So 14 plus 24 gives us a total of 38. So this will be this value here. And then finally, 2 times 3 is 6. Plus 6 times 8, which is 48. So 48 plus 6 gives us 54. This means when I go to write my final matrix, I will place a 27 at this position, a 38 at this position, a 43 at this position, and a 54 at this position. And that is going to complete my new 2 by 2 matrix, which I achieved by multiplying these two 2 by 2 matrices together. So you might be thinking to yourself, why do I care about matrix algebra in a chemistry class? I thought we were learning about chemistry and molecules. And that's true, we are. However, remember, we have recently been talking about and learning about in this class the fact that you can manipulate molecules in 3 dimensions and change their location. In truth, when you do that, what you're doing is actually performing a transformation matrix. So let's consider the fact that in 3-dimensional space, we have a molecule that lies at some x, y, and z coordinates, typically assigned arbitrarily, but we can pick a frame of reference to serve as our origin. And then every molecule must lie, since we live in a 3-dimensional world, along some 3x and x, y, and z coordinates. In fact, let's consider one of those such examples. So if we were to place a water molecule, which looks like this, somewhere in space, then they would have x, y, and z coordinates. And those x, y, and z coordinates can be represented as a 1 by 3 matrix with some values of x, y, and z. And we could perform some sort of symmetry operation, for example, which would give us a new set of coordinates following whatever transformation that is. And I think the easiest one to start with is going to be that C2 rotation. So remember, a C2 rotation is when you rotate 180 degrees along some principal coordinate axis. And the convention is to always assign the principal rotation axis as the z-axis. So that's why I've placed the z coming straight up from the oxygen, because that will serve as our z-axis with which we can rotate 180 degrees to give us some new position. So for example, if our original hydrogens were 1 and 2 like this, then following a C2 rotation, the molecule still looks the same. However, the oxygen has remained in place, but the hydrogens have flipped since we've done a 180 degree rotation. So now let's think about what that means as far as what has happened to our original x, y, and z coordinates, and we can use that to generate what our new coordinates might look like. So remember, when we do that C2 rotation, we're rotating along that z-axis, and therefore, by definition, that z-axis is remaining unchanged. So our z-axis will still be the same before the transformation and after the transformation. If we're to think about the other coordinates as some vector along the x, y, and z axes, then we can see what happens to those vectors following a 180 degree rotation. And hopefully you can see that if we were to rotate that and take a look at this x vector, then that x vector after a 180 degree rotation is now going to be at negative x. So whatever was at x originally, after a 180 degree rotation along the z-axis, has now become negative x. So that's going to be the value following that C2 rotation. Similarly, the y-axis, if we're to consider that as a vector as well, following a 180 degree rotation will now be negative y. So we can say that that would be negative y. And I could do that qualitatively just like I did. However, I could also do it mathematically if I remember that. Remember, what we would do is we would take some matrix, multiply the rows by the columns of two different matrices to give us these values. So now let's work backwards and see what that C2 transformation matrix actually looks like. So the easiest one to do is to start with the z-axis. Remember that when we do this, we need to multiply the rows by the columns. So if there is a value here, then it would be multiplied by x. If there was a value here, it would be multiplied by, added to the multiplication of y, and then we would add whatever value is here to the z. So therefore, since my final matrix can't have any x's plus y's or anything else, it just needs to be z, then those first two values should be 0. And my final value of what is going to become a 3 by 3 matrix should be a 1. So we would have 0 times x is 0, plus 0 times y is 0, plus 1 times z, which is going to give us that z. And now we can do the same for our x and our y coordinates as well. So x, being the first position, I need to multiply some number by x and eventually end up getting a negative x. And that value is negative 1. So if we multiply negative 1 times x, that gives us negative x. I don't need any y's or z's here, so my next two values should be 0. And again, that'll give us negative x plus 0y plus 0z just gives us a negative x. And then similarly, we should have 0 times x plus negative 1 times y plus 0 times z to give us negative y. And in fact, this is the way that we derived the transformation matrix for a C2 symmetry operation. And you could do the same for all of the symmetry operations that are possible. Inversion, mirror planes, etc. They all have some transformation matrix that will confer some operation on x, y, and z coordinates or the position of a molecule to give us new coordinates. In fact, let's do this for one more simple example. Remember that every molecule in the universe has some amount of symmetry. The easiest symmetry for everything is going to be the identity matrix. Remember, the identity operation, we give the symbol E, and basically it should leave the molecule completely unchanged, meaning that the coordinates should remain identical. So in order for x, y, and z to turn into an x, y, and z matrix, we should have a 1, 0, 0, because 1 times x plus 0 times y plus 0 times z is equal to x. Then we should have 0, 1, 0, because 0 times x plus 1 times y plus 0 times z equals y. And then finally, we should have 0, 0, 1, because 0 times x plus 0 times y plus 1 times z equals z. And this is the identity matrix. These are all of the transformation matrices that are possible for the C2 point group, which is the same point group that water molecules lie in. The identity matrix, the C2 matrix, the sigma v, and the other sigma v in the xz and the yz planes respectively. Each of these represent a 3x3 matrix, which would give us the transformation of that symmetry operation. And these together serve the basis for what is called a character table, which represents all the different mathematical functions that are possible for an object in that specific point group. So for example, for that C2v character table, we would find that it would contain rows and columns which contain the E symmetry operation, the C2 symmetry operation, and both of the sigma v's, one for the xz plane, and then also a sigma v for the yz plane. And if we're to block diagonalize each of these matrices, which means take the simplest 1x1 matrix that represents the entire matrices, then we can figure out what is the reducible representation for the C2v character table. So when we block diagonalize or simplify into 1x1 matrices, we can take just the ones with values. Like for E, this would be the block diagonalization. And then if we're to add 1 plus 1 plus 1, we would get a 3 under E. And this value that goes inside the character table is called a character. And a character is defined only for a square matrix. So it would have to be a 3x3 or a 4x4. It has to be a square matrix. And it's the sum of the block diagonalize along that diagonal. So 1 plus 1 plus 1 is 3. Similarly, for the C2, it would be negative 1 plus negative 1, which is negative 2, plus a positive 1, which gives us a negative 1 overall. 1 plus 1 plus negative 1 gives us a 1 for this character, and then negative 1 plus 1 plus 1 gives us a 1 for this character. And we call this the reducible representation for the C2v character table. And we call it a reducible representation because we can actually simplify it into even more simple terms, which we call the irreducible representations. That reducible representation can be represented by the symbol capital gamma. This reducible representation is made up of some number of irreducible representations which are more simple terms. Consider these, which I've gone ahead and written out, which correspond to the x, y, and z coordinates, and which we'll talk about how I derive these in just a second. But let's see that if we were to add the column for E, we would get 1 plus 1 plus 1 is 3. Negative 1 plus negative 1 plus 1 is negative 1. 1 plus negative 1 plus 1 is 1, and negative 1 plus 1 plus 1 is 1. So notice that these do align, allowing me to combine them in some fashion, and since I'm combining irreducible representations, I make a reducible representation. So these cannot be further reduced, but they can be combined to make up the reducible representation. So always the reducible representation is made up of some number of irreducible representations. And that's going to be an important concept coming forward, so I'll say it again. The reducible representation is made up of some linear combination of irreducible representations. So the way that I got these values actually came from the previous screen where you would have seen the actual transformation matrices. If you looked at the block diagonalization for identity, for example, they were all 1s, which is where I got these. If you looked at the C2 rotation, remember the x and the y changed to the negative x and y, and the z stayed the same. And then similarly for the sigmas, I got it from the block diagonalization. Importantly, these aren't all the irreducible representations that make up the C2V character table, and we're actually still missing some, which we'll talk about shortly. So this is the full character table for a C2V point group. Now, importantly, in chemistry, we're obviously talking about molecules, but group theory comes from a field of mathematics, so it doesn't necessarily have to be talking about molecules, and therefore there may be information in a character table which is irrelevant to considering things inside of chemistry. However, here we see a ton of information, and I'm going to try to walk you through the anatomy of a character table so that you can start to understand what each of these symbols mean. Remember that the numerical values inside of the character table are actually called characters, and they tell you something about whether or not something is symmetrical with respect to something else. For example, anytime you see the symbol A on this row of what are called Mulliken symbols, again, those are called Mulliken symbols, which are actually the way that we represent the irreducible representation. So remember, anytime you put irreducible representations together, you can make reducible representations which had capital gamma. Those irreducible representations we depict with Mulliken symbols. Anytime you see the A symbol, that means that with respect to rotation around the principal axis, that thing is symmetrical. So for example, for the A1 and the A2, notice that there are positive 1 characters underneath C2, because if you were to rotate 180 degrees, the molecule would look the exact same. Therefore, we would say it's symmetrical with respect to rotation around the principal rotation axis. Notice then that the next two have -1 values, which means that they're unsymmetrical with respect to rotation around the C2 axis. Those get the Mulliken symbol of B. There are also other Mulliken symbols. For example, one that is commonly seen is going to be the E Mulliken symbol, not to be confused with the identity operation. And it actually means that things are doubly degenerate, meaning that they transform with the same energy. Similarly, the symbol T corresponds to triply degenerate, and we'll see more examples of those further in the semester. We're also going to see other Mulliken symbols, but for now in the C2V point group, these are all that exist, so we'll talk more about Ungerada, Gerada, E and T further later on in the semester. What you should also see in this character table is that there are an additional 2 columns which don't contain characters or symbols. These actually correspond to different types of mathematical functions, specifically linear functions and quadratic functions. So these are linear and quadratic functions. Now in math, when we're talking about coordinates, we talk about in 3 dimensions the x, y, and z coordinates. Importantly though, for chemistry, when you think about an orbital, for example, the px orbital lies along the px axis, and therefore as chemists we use character tables to identify what is the irreducible representation that might correspond to a px orbital. And for that we'll use these linear functions and see that the px orbital actually corresponds to the b1. So the px is a b1 irreducible representation. And let's take a look at what that might mean. So if this was the z-axis, notice that if you were to rotate 180 degrees along the z-axis, the shaded region goes to where the unshaded one was previously. Therefore, we would say that it doesn't look identical. In fact, we would say that that's unsymmetrical because they are the inverse of one another. And that would get a character of -1, just like it does here. We skipped over identity because remember everything stays the same, which is why all the values in this first column are 1. If we were to do a sigma v, or inside the plane of the screen, a mirror reflection, remember this orbital would look identical. So this also gets a character of 1. However, if we were to flip and that mirror plane is actually in between the two lobes, notice then that if you did a mirror reflection, you would flip the phases and that would be unsymmetrical because they would be the inverse of one another, which is why it gets a -1. Notice that that transforms like a px orbital for a molecule, which is why there's an x here. The capital R sub x, y, or z values actually correspond to rotations. So later on in this class, we're going to talk about spectroscopy, looking at things like linear, rotational, vibrational spectroscopy, and the R's actually correspond to rotations about some axis. Rotation about the z-axis, rotation about the y-axis, or rotation about the x-axis. And then notice that there's another column that corresponds to what are called quadratic functions, and what you should see is that these kind of look eerily similar to the d orbitals. The dxy, the dxz, the dyz. They also help us identify whether or not something is polarizable, which we'll talk about later in this class. Let's talk about a few more features of a character table. We can determine the order, which is the total number of operations possible for a specific point group, which in the case of C2V, we see that there's one identity, one C2, one sigma V, and one sigma V in the YZ. This means that our order, which is given the symbol of H, is equal to 4. When we separated the symmetry operations, we placed them into classes. For C2V, it turns out that there's only one type of operation for this molecule, but occasionally you'll see some sort of exponent or coefficient in front of those values to indicate how many operations lie within that class. Common examples of this are things that have multiple C2 axes, so you would see some number times C2 to indicate that there are multiple operations within that class. And it actually turns out that in order to prove that this character table is appropriate, the total number of irreducible representations, which just so happens to be 1 plus 2 plus 3 plus 4, needs to equal our order, or the classes needs to equal the total number of classes. And occasionally the number of classes will not equal the number of order, so we need to keep that in mind. In this case, they do equal the same. There are 4 irreducible representations, 4 different characterizations for classes of operations, and it just so happens that since each one is a 1 coefficient, the order is also equal to 4. Another mathematical proof for proving the construction of the character table is called the sum of the squares, where you actually take the sum of the squares of all of the identity operations, or for any of these really, and it should equal the order. So 1 squared plus 1 squared plus 1 squared plus 1 squared equals 4. In this case, that equals the order, so we know that this character table is correct. It also turns out that each irreducible representation needs to be what's called mutually orthogonal, meaning that if you take the cross product of each of these, they should give you a value of 0. And we can just pick 2 examples to quickly see this. So let's say we wanted to see if B1 and B2 were orthogonal to one another, meaning that if you take the cross product, they equal 0. 1 times 1 is 1. -1 times -1 is also 1, so now we're up to 2. 1 times -1 is -1, so 2 minus 1. And then also -1 times 1 is -1, so 1 minus 1 is equal to 0, so we have proved that those are mutually orthogonal. And then also, for every single character table, you're always going to have a perfectly symmetrical irreducible representation, where the top row actually corresponds to characters that are all equal to +1. In our class, I'm not going to make you derive character tables. However, if you go on to graduate level inorganic chemistry, you may be expected to completely derive character tables and prove that once you have, that they are actually based in reality and you can prove them mathematically. If you learned anything in today's video, make sure to give it a thumbs up and drop a comment down below if you have any questions at all related to group theory, symmetry, or character tables. And don't forget to subscribe, and I'll see you in the next video.